What is up, multivariate gang? We are going to be continuing our discussion of vectors as we discuss vector subtraction. So what is vector subtraction? Well, we know what scalar subtraction is. 4 minus 2 equals 2 and all that. And in the same way, we can subtract our vectors. But before, we need to know exactly what a negative vector is. All right. So we have our number line, right? 0 in the middle, and let's just talk about 3 and negative 3. All right. So we have 3. 3 is 3 units to the right of 0 on the number line. And what we do when we add a negative is we go to the left. We keep its magnitude, which is 3, but we switch directions to the negative direction. Well, with vectors, it is the exact same. If we have a vector A, and let's say it goes 3 in the x, 4 in the y. That means that vector negative A has the exact same magnitude, but goes in the exact opposite direction. Now, in terms of its x and y components, how does that happen? Well, as you can probably tell by looking at it, this guy's negative components. This guy went forward in the x, so he has to go backward in the x, exact same amount. This guy went forward in the y, so he has to go backwards in the y, the exact same amount. Cool. All right. Now, when you are subtracting a number, another way to interpret subtraction is the addition of negative numbers. And in the exact same way, we can interpret the subtraction of vectors as the addition of negative vectors. All right, so let's do it. We've got a vector A. He'll be 4, 2. Those will be his components. And we've got a vector B. And negative 1, 4 are his components. So if we want to find the vector A minus B, all we got to do is find negative B, which in this case is this guy right here. 1 forward, 4 down. And then we draw our resultant vector. From the tail of the first to the head of the second, just like we do with addition. Bam. All right. Now, geometrically, there is another way to interpret this. You can either think of it as from the tail of the first vector to the head of the negative vector, or you can think of it from the head of this vector to the head of this vector when they're tail to tail. Let me show you. So, if I took this vector and I put it over here, there, I put their tails together. I gave them the same initial point. Whoops. Sorry, guys. I could move this vector right there. And it looks a little bit off because I'm bad at drawing, but they're the exact same. So this guy is also vector A minus vector B. So geometrically, we've got two things going for us here. We've got A plus negative B, and we've got head of the second to the head of the first. Easy enough. Okay, so numerically, what are we doing? Well, as you probably guessed, if we have a vector, we're going to leave it in 2 dimensions just to make the writing easier for me, but the exact same takes place in 3 dimensions. AX, we've got a vector A that equals AX and AY. We've got a vector V, vector B that equals BX and BY. And then A minus B, which is the same as A plus negative B, going to equal AX plus negative BX AY plus negative VY, which equals AX minus BX BY, nope, AY minus BY. So you subtract the 2 vectors, you subtract their components. Easy breezy. All right, example problem. Find the vector v minus w, and vector v equals 1, 4, 7, and vector w equals 3, negative 2, 3. Well, v minus w equals vx minus wx, vy minus wy, vz minus wz, which is equal to 1 minus 3, 4 minus negative 2, and 7 minus 3, which gives us negative 2, 6, and 4. Sweet. Hopefully no problems there. I'll see you guys later when we discuss scalar multiplication.